My name is Gaurav Chadda, and today we're going to talk about warehouse and Lakehouse analytics in MySQL HeatWave. We have heard today, and we will continue to hear more today, is that data comes in a lot of different flavors and volumes, right? This is what we try to call the pyramid of data. At the tip of the pyramid is our transactional data. It is mission critical, it is business critical, but the volumes tend to be lower. Beyond that, we have analytical data, where the volumes can be large. You have to do large scans, large joins. The volume of the data tends to be a little larger. Moving on, we have a lot more data we want to do machine learning on. We have data in the object store, where the schema might not be present in the data. Data could be coming from sensors, from IoT devices, from drones, and it might be semi-structured, it might be unstructured, and so on. And that is data living in data lakes or object store. And even a bigger world of data is what we call unstructured data. And you've heard today already some solutions that we have come up with to be able to derive insights from this unstructured data. This is the world of proprietary documents, of images, of songs, and what have you, right? And what you can see is the data volume just keeps on growing. You can call it the pyramid of data, you can call it the iceberg of data. And a lot of the data is not neatly categorized or stored in production databases and easily queryable. And through this presentation, we'll try to look at what MySQL HeatWave can do to derive insights and make it available for querying. So we've seen this diagram here before. MySQL HeatWave is the one-stop shop for analyzing data that can come from MySQL storage, like InnoDB storage engine. This is a structured, nicely categorized or relational data. The data could come from object store as well. This is data in CSV files, in Parquet files, exports from other databases. So this data can also be ingested into MySQL HeatWave and queried like any other MySQL data. It is important to note that when data is coming from an external source like object store, this data is not copied into a MySQL storage engine. It is ingested into our in-memory HeatWave's cluster, but available to query just like any other MySQL table. So we've heard and we know of and we love many connectors, tools, and the vast ecosystem that is present around querying and interacting with the MySQL tables. All of that will work pretty much out of the box. So the power of that is hard to overstate rather. That you can have just files that were just lying around, and it was hard to derive valuable insights from it, or hard to do analytics on it, hard to benefit your business from it. But now with MySQL HeatWave Lakehouse, you can ingest that data and just query it. Where does this data come from in object store? The data comes from, as I said, enterprise applications. It can come from your IoT devices. It can come from Spark streams. It matters very little where the data comes from. It can come from a variety of sources, and MySQL HeatWave can ingest it just the same and make it available for querying just the same. We have strived very hard to make it extremely performant and extremely competitive. So performance is one thing where we excel, and we have shown we're not 10%, 20% better. We are multiple times better than the competition in performance. Where we excel even more and really shine is price performance. And as we've heard Nipun and Wim mention before, in the public cloud and the cloud, price performance is king. And that's where we shine even more. And you can see the numbers. It's 20x better. It's 60x better than the most competition out there. But we're not sitting on our laurels, and we are continuing to provide even more analytical features that are becoming more prevalent in the tools and industry today. These are operators like cube, like hyperlog log. These operators are now added to HeatWave and offloaded to HeatWave, performing extremely well, and just makes writing queries and deriving insights from this data extremely easy. So you can see, I mean, a lot of competitors support a subset of it. Now we are supporting a very large set of these analytical operators as we're continuing to add it more and more over time. So that was for data really in MySQL database. But a lot of the data, as I said, is not in databases, it's in object store. And this is a stat from analytical, from analyst, where they posit that most of the data being generated and stored is outside of databases. And that is for a number of reasons, right? It can be cheaper to store it outside of the database. You may not immediately have a value that you can derive from it, so you store it out of databases. You store it in object store. And that's why the immense growth of data is not necessarily stored in expensive or structured databases. It's stored in object store. And that's where we come up with HeatWave Lakehouse, where which I just mentioned, we can ingest data from object store and make it available for query. I show a very brief example, pseudo example of how to create a table from this data in object store. You can create the Lakehouse table very similarly to any other MySQL table. You can just point your create table DDL to the data in object store. It can be a prefix, it can be a regex, it can be whatever, just like accessing a file system, and create a table. And once it's created, it's a very familiar syntax. Once it's created, it behaves like any other MySQL table. It's 100% compliant with the standard MySQL syntax. You might be wondering though, if my data is not in a database, it's just in files in the object store. It's coming from a drone. It's coming from a temperature sensor. How do I know what the scheme of the data is? It could be a Spark stream. It could be another application that that is just exposing metrics. What is the schema of this data, which is required to create a MySQL table out of it? And that's where we provide this amazing schema inference capability in MySQL Autopilot. What we do here is we go ahead and sample the entire data set. Now, this data set can be very large. It can be hundreds of terabytes big. And if you so choose, you can go make Autopilot go over the entire data to look at its schema and try to infer it. But what you can do by default is sample the data, or rather, Autopilot will do it for you. It will sample the data and infer the schema of the data and return back neatly packaged as create table DDLs that you can just execute and create a table out of this data that is lying in object store. Here we not only look at this, and the schema you can see it's not only data types, it's data precision, it's the width of the varchars. And if the names are available of the columns, we'll extract those as well. The names can be in the header of a CSV, it can be in binary formats like Parquet, and we will be able to extract all of this and neatly package it as a create table DDL that you as a user don't have to write it out. What is important to note here is that even though the data may be coming from different sources, it could be coming from the MySQL database into HeatWave, it could be coming from object store into HeatWave. The performance of queries does not change. So you give up nothing on as far as query performance is concerned, no matter where your data is coming from. As you can see, whether in this example, this is a 10 terabyte TPCH database, whether the data came from HeatWave, which is the MySQL database, or it came from Lakehouse, from object store, the query performance GeoMean remains the same. Also, it is much better, multiple times better than the competition out there. So, that was an example that I gave for 10 terabyte TPCH. As I said, object store data or data lake data spans tens of terabytes, hundreds of terabytes large. So this performance advantage that we have over the competition does not diminish. In fact, it becomes more when you scale the data even to larger sizes. So if we can scale the data to up to 500 terabytes, and again on TPCH database, you can see that we are highly performant, much better than the competition. So we're not giving up that lead on performance. We scale extremely well across 500 nodes plus to get this performance. We have supported structured data file formats in Lakehouse. CSV, Parquet, Avro, these are the most popular formats out there for analytical processing, for storing data out of Spark streams and other devices. But we're extending this support now to semi-structured data, which is present in JSON. And JSON can be present in any of these file formats I already mentioned, CSV, Parquet, Avro, and so on. It can also be just JSON files. And we have now added support for new line delimited JSON files natively in HeatWave Lakehouse. So once you have ingested the data into Lakehouse, you can also ingest JSON data, then you have to query it. You have to query it using JSON operators. So together with being able to ingest JSON data into HeatWave, we have now implemented and accelerated versions of JSON query operators. These JSON query operators will get offloaded to HeatWave and give you the same performance benefit, the same scale-out capabilities that we have for all of the other SQL operators. So up till now, HeatWave Lakehouse has been able to load a snapshot of your data. Now, if your data changes, new files get added. Maybe you want to keep only the last 30 days of data in your table. A new day rolls by, and you want to drop the 31st day of the data and get the newest day's data into HeatWave Lakehouse. You can do that now with what we call the incremental data load in HeatWave Lakehouse. This is here the unit of change for data present in a Lakehouse table is one object. So an object could be added, object could be deleted, could be updated. And if you are aware of how object store works, an update of an object is essentially can be modeled very simply as a deletion followed by an addition. With this incremental data load, we will always be able to provide a one-to-one mapping between data that is present in the HeatWave Lakehouse table and the data that is present in the user bucket in object store. We only load the delta from the last time you have loaded. So if you have loaded some data already and you add one more object, or you add 100 more objects, we'll only load the delta. If you have deleted some objects, it is a very fast in-memory operation to just get rid of them. And we maintain transaction semantics. We maintain read committed and snapshot isolation for getting this data, incremental data, into HeatWave Lakehouse. The interface to do that, the user can choose when to incrementally load the data. So the user may or may not want to do this too frequently. It's completely up to the user. They can choose to do it every minute. They can choose to do it every hour, every day, whatever frequency they feel like. And it is integrated into the existing stored procedure that we have, which we call auto-parallel load or HeatWave load. It is a simple option to say, OK, you have this table loaded, refresh it with whatever data has changed. The way we do it is we treat each object as like a horizontal slice or a shard of the table. New objects come in, new horizontal slices of the data get added in. Data gets removed, those horizontal slices of the data get removed from in-memory. And the new data that needs to be added scales out just like the initial load. We can distribute a single object across 500 nodes and load it. There is no limitations on that. So the benefits of fast ingestion of object store data into Lakehouse, HeatWave Lakehouse, is maintained here with even incremental updates. And we've added another feature. Here we preferably execute all queries on HeatWave. But as you've heard before in the earlier talks, that we want to be able to execute JavaScript stored functions on the MySQL server. Now you can execute that coming very soon. Now you can execute JavaScript functions using GraalVM on Lakehouse data as well. And we enable that through data being piped from the HeatWave cluster to the MySQL node, where the GraalVM and the JavaScript functions execute. So that feature now is available for data lying in object store as well. And AutoML, this is an existing feature which we have now enhanced, where AutoML can also be run on data present in object store through HeatWave Lakehouse tables. This is a very rich suite of machine learning capabilities that we have in HeatWave, and this now is extended to HeatWave Lakehouse data as well. We've heard a lot about vector types and vector store today. So let me tell you a little more about it and how we have added it to HeatWave and HeatWave Lakehouse. So a vector data type is essentially an array of numbers, floating-point numbers, and this has been added as a native data type in MySQL. We have also added processing functions, vector processing functions that can work on that vector data. These are distance functions like dot products, cosine, distance functions, and a lot of work has been put in to use native SIMD instructions present in the underlying architecture to accelerate this. This vector processing functions, they execute at memory bandwidth across the entire HeatWave cluster. And so what part of this data is actually brought in? We have been on this journey from OLTP data that is managed very well by MySQL. We've moved on to analytics data in HeatWave, to data lake data or object store data in Lakehouse, to semi-structured data in JSON. And now we can process unstructured data present in proprietary documents like PDFs, like Word docs, PPTs. And this all can be brought into a HeatWave cluster. For unstructured documents, what we do is we're interested in part of the data, right? We're interested to start with. We will parse out the text, and the different elements, the different data modalities present in these unstructured documents. We will treat them separately because we need different embedding models for each data modality. Text is different, images is different, and create vectors. And once the vectors are created, we will put them into a Lakehouse table, which we call a vector store table. This end-to-end ingestion pipeline is built in to HeatWave. This does not require any information or any expertise from the user side, which embedding model to use, how to extract the data or parse these proprietary documents, how many nodes to use. And so all of this is completely hindered and completely integrated into a HeatWave Lakehouse table load. And it works just like any other Lakehouse table load. You point the MySQL table definition to your data, and you do a load. And the rest is figured out automatically based on what kind of document formats we see. And we have maintained this ethos of being extremely performant, using the cluster as well as we can, and that continues on with vector store ingestion as well. We are able to parse and segment the data and create vector embeddings in a fully scale-out fashion using every core on every machine that we have in the HeatWave cluster. What is important here is because we have integrated this pipeline in HeatWave, we are able to marry the different phases of this ingestion pipeline so that they work well together and they're optimized to work well as an end-to-end pipeline. So the parsing and the segmentation, the batch size we need to create embeddings out of it, all of it is tuned in a vertically integrated fashion. As I said, we have created these vector distance functions to work on this vector data types, and this works at memory bandwidth. So once you've ingested this unstructured data into vector store, what do you do with it, right? You can write, as I said, you can write SQL queries to run vector distance functions and find the segments or the documents that are most similar to the input to the input text. Or you can integrate it with our existing AutoML pipeline. So you can marry our recommendation system in AutoML with a RAG query from this vector store to create more context and combine these queries. We have some integrated solutions that Nipun already spoke about in the previous talks, but it is available to be used as the user wishes because they can query the vector store natively using native SQL syntax. I have some example queries here. You can, as I said, you can create a vector store just like any other Lakehouse table load. And you can query it using native SQL syntax. We've added native SQL functions to do that. So you can create your own application. You can combine your OLTP data, your analytical data, along with this now new category of unstructured data with the vector embeddings which capture semantic meaning of your documents. Or you can use our stored procedures that we have written to create an end-to-end application. We call them MLRAG. And there are talks, I think at 3 p.m. that will go more into detail of that, and I encourage you to attend that. One of the examples of what you can do with this now vector store is you can have your proprietary documents. These could be research papers, these could be manuals, these could be PPTs someone created in your organization. And we can ingest these into a vector store and then start asking questions. The question, the pipeline here, I'm not going into too many details here, but when you ask the question gets embedded using the same embedding model. We look up the context using a RAG query on the vector store to find the most similar segments from whatever has been ingested, and it gets output as context to an LLM which summarizes the answer. So the answer is very relevant. It is coming from your documents, from your data. It never leaves the HeatWave DB system. So let's put it all together, right? Data stored in databases or data stored in files, right? Data stored we can query both in a highly performant and a price performant manner. You want to run ML on it, or you want to run GenAI on it. We enable that as well on the same data in the same DB system. There are ways to put all of these functions together using a multitude of products and creating expensive, complicated ETL and data pipelines. But we do all of that in one integrated solution, and it helps us actually get better performance and better efficiencies because we can tune each stage of this pipeline, knowing what came before and what comes after. And we make it available not just in OCI, but natively in AWS and through our interconnect in Azure. With this, I want to just go over a small example of a sample use case where the whole power of MySQL HeatWave can really help. So let's assume you have IoT events coming from sensors or drones. These can be metrics like temperature, like torque, spin. These could be metrics about the health of these sensors. How many times have they transmitted a reading in the last hour? And this data is output typically in some CSV or JSON, or it could be image data that a drone takes images of crops or something. All of this data is typically not written in a database. It's typically going through to objects in Object Store. What do we want to do with it? We want to understand any anomalous hotspots. We want to understand if any of the health metrics of the system are showing any wear and tear. If there is a part that's going faulty, we want to understand where can we order this part from, which vendor will have this parts. And this is structured data in your MySQL table. We can also predict which parts might fail soon. These are challenges. The challenges to do that is you have to ingest all this terabytes of data. This data will be present in different file formats. The query should happen quickly so that we can run this query again and again at the event of a trigger. We might want to run an ML model to do some predictive maintenance. And we want to marry this data or join this data with ERP and SCM data to understand which vendors have these parts, and we can order soonest. These challenges that I've described are all solved by the MySQL HeatWave DB system, and which I've described in this presentation. With this, I'll wrap up, and thank you for listening.